and we're going to resume our sessions with a talk on quantum chemistry from a longstanding collaborator of ours, Dr. Glenn Martyna from the Pimpernel Science on projected augmented wave-based Kohn-Sham Density Functional Theory in OpenAtom with n squared log n scaling. Thank you, Glenn. Go ahead and begin when you're ready. I'm not currently hearing you if you're speaking.
Can you hear me now?
Yes, yes.
And you can see the screen?
Yes.
All right. Thank you for inviting me, guys. I'm going to talk about a long-term collaboration with Sanjay and Eric and the guys, in particular, a former postdoc of theirs and a former postdoc of mine, Raga and Chi and Eric. Okay, so the goal of our collaboration is the study of complex heterogeneous systems with the goal of discerning new and emergent physics and creating impact in the field. So we've done things to invent new transistors that are based on pressure switching. We've looked at antimicrobial peptides and how to design them. We've looked at DNA sequencing and solid state nanopores. And we've looked at advancing the technology in solar cells. Our approach is basically coupling hardware, software, and new methodology coupled to physics-based solutions for complex systems. Pretty much like all the talks we've heard, there's this melange of opportunities that this synthesis creates. So we have a code called OpenAtom, where the key for us is not to do small systems that we minimize, but to do large systems where we are worried about atoms and molecules moving at finite temperature in complex environments to understand the physics. So if you think about an antimicrobial peptide near a membrane, it's not a single configuration that matters. It's fluctuating. How it interacts with the membrane or enters the membrane is highly fluxional. If we think about pollutants, we need to worry about linking a dye molecule to the pollutant, worrying about what the spectra is, and that will require some new capabilities in OpenAtom. And if we want to understand chemical reactions in dense arrays, for example, to understand failure modes, then in novel solar cell materials, we need to. So this will be done by OpenAtom, as I said. So it's a long collaboration between myself, Sanjay, and more recently, Sarab Ishmael Begay. And we built electronic ground state and excited state parallel software and methods to take these configurations that the code generates and also calculate spectroscopy. So without any one of the underpinnings, we're in more trouble. So we do have a long-standing collaboration. So we have lots of what I would say exciting results. We've taken a rather large system, a metal organic framework, and we've scaled it on Blue Gene Q. We've taken, again, a rather large aqueous system on Blue Gene Q and scaled that down with markedly improved performance compared to other people. So again, that's electronic structure, atoms moving on the electronic ground state. And we can do it faster than other people. We've also done some methods development to reduce the scaling of things like exact exchange. And I'll tell you about our new projector augmented wave to allow us to study metallic systems. The electronics excited state work, which is led by Saurabh, you'll hear about next. We've done a highly scalable calculation on, again, blue gene. That's led by his group, where we achieve much higher scaling compared to other people. And we've also recently developed an n cubed method, where n is the number of electrons in the system. And that paper just came out in this year on the method, and the parallelization will be presented next. So, and that software will be released, and you'll hear all about that next. So when we talk about solving electronic structure in physics, one of the big workhorses is Kohn-Sham Density Functional Theory. And Kohn and Sham were two famous gentlemen. Kohn won the Nobel Prize, though he's a physicist. He won it in chemistry. And what he showed was an existence proof, is that if we have the electron density, we can in fact find the electronic energy, and the ground state energy is simply the functional minimization of the kinetic energy of non-interacting electrons, the electron-electron interaction, the external potential, and the sins, which take into account the fact that electrons are fermions, so we have exchange, and correlation basically corrects the self-interaction in one of the first terms, and the fact that we use the formula for non-interacting electrons. We typically, in our code, we have an exchange correlation function, which is where all the sins are hidden. That depends on the density and its gradient. So it is an approximation because Kohn gave us an existing proof. What we use in our code is a plane wave basis set. And what's great about plane waves is they're everywhere, and they're pretty unbiased as to the position. They're unbiased as to the position of the atoms. However, since they don't know about the atoms, this approximation can cause difficulties. Nonetheless, what we've able to do is take every single routine except orthogonalization and get it to scale as n squared log n or better, using Euler exponential spline interpolation, which I'll explain. N is the number of electrons. So it's highly parallelizable, as we discussed before, under Charm++, and we have lots of capabilities to move the atoms around under the forces produced by this ground state approximation, and we can also treat spin. So the disadvantages I hinted at is that because it doesn't really know, plane waves really don't know about the atoms. They're simply delocalized waves in which we expand the electronic state. You require a very, very large basis and very large memory. And if I have atoms with cores around them, say iron or nickel or copper, you need an intractable number of basis functions. So what we've used the code for very successfully is first row, second row elements that don't have giant cores. So if we want to move on and study more metallic and complex systems, we need to do better. So in the 90s, Peter Blüchel wrote down a projection operator-based approach, where what he tried to do is introduce the core, and we'll talk about that in detail. So we split the states into a localized piece, which is new, and a delocalized piece, which we treat with plane waves. So because we now have a core, we can do NMR and linear response theories that require the core easily. And it reduces the memory requirement because we have an explicit treatment of the cores. So what we had to do, as we did for the plane wave code, is get all the methods except for orthogonality down to n cubed, down from n cubed to n squared log n, improve the parallelization, and improve the accuracy. And we'd like to implement that in OpenAtom. So as I said, Blüchel's genius here was to take the electronic states and divide it into two parts. The smooth part, which is the plane wave part, and some core part, which really does know about the atoms. And the core really only lives in a small region of space around the atoms, and these regions don't overlap. So here's your plane wave part. We expand this smooth part in plane waves. It lives everywhere, even inside the cores. And then we have a projection operator based approach, which preserves the rotational invariance of the wave function, which is a fundamental property. So it's related to the overlap of the projector with the wave function. And what it effectively does is it switches out the soft plane wave core with a real core here, but through a subtraction, which is why this projector is written as a difference. So what you end up with is jello and fruit. So you have state I, he's in atom 1, state J, that's for atom 2, and so on. And then you have the smooth part that lives throughout the box. So that is a big improvement because we have an explicit representation of the core while keeping the joys of plane waves in their very nice unbiased convergence. And we preserve through the construction the basic properties of the wave function. So what we have is a functional that looks like the non-interacting electron kinetic energy, which is just del squared on these states. We have the Hartree term, which is the interaction of the density exchange correlation and some external interaction, which here we just write as Coulomb's law. So all these terms will now have three parts. We'll have a smooth part, a part that only depends on the stuff in the core, and a part that depends on the interaction between the smooth part and the core part. And that's true for all these things. So we have a smooth exchange correlation function and then an exchange correlation function which depends on things in the core. So what we have is a mixed basis set with a delocalized piece and a localized piece. So in some sense, it's a natural multigridding. That said, there's no truncation scale for the long-range interactions. If you notice these sums, they go over all the periodic images. And 1 over R, that never can go away. You need to choose a boundary condition and do things properly. So we use two tricks, two things from mathematics. An algebraic identity from Ewald, where 1 over R is equal to the ERF over R plus the complementary error function. This splits these terms with Coulomb's law into two parts, a long-range part and a short-range part. We can take the long-range part into reciprocal space, and all these terms can now be evaluated with error control based on one parameter alpha, which is simply the splitting of 1 over R into a long-range bit and a short-range bit. So this was left out of Blüchel's original formalism, and you didn't have the accuracy control you would really like. So how does this work? We have a long-range cutoff and a short-range cutoff. There's a relationship between them. And if I look at a plane wave cutoff and what kind of distance I need to compute the short range interaction, I can get very, very high accuracy with a very small plane wave cutoff. Now this is only useful because in effect, what we've done is we have an explicit representation of the core where I can do all these core integrals with a very small cutoff. So there's a cutoff for the plane waves to understand details of the wave function, which we've truncated, which we now have core parts, so it doesn't need to be as big, and we have accuracy control. So that's a beautiful new feature that we've added to PAW, which really helps the cause. And it's important that both the cutoff radius and this G-space cutoff are relatively small. So there are two tricks you need to understand plane waves. So the first is that we work with a finite cutoff, and therefore we have a discrete variable representation. And what that means, if I want the Fourier coefficients of the second power of a function in real space, I can just take the number of points equally spaced. I could square the function, take the FFT, and that gives me the exact result. I can also go back and forth between real space and G space with FFTs exactly because my basis is finite. So that's called a discrete variable representation, and that's been known forever for plane waves. Everyone uses it. The more new wrinkle is not really new, but it's by Euler. And what Euler said is if I have a plane wave evaluated at a point S, which is not a grid point, I can express it as an interpolation from the equally spaced grid with a controllable error. So this will allow us to do things like take our plane wave and put it into a little sphere of points around each atom with a controlled error. We'll also be able to calculate our overlap integrals, which require the positions of the atoms, which define the coefficients of expansion of the core parts with high accuracy. And because we're using FFTs, we can do them in reduced order. Now, this is going to be a multi-grid problem. We have a grid to do Euler exponential spline to calculate overlaps. That's one grid. To compute the density as per point one, which is the square of the wave functions, the sum of the squares, we need a density for that. And to calculate the Coulomb interactions in n squared log n, we need a density Euler exponential spline. And we have those first three grids in OpenAtom. We need one more for the discrete spherical polar grid around each atom, which is all new. And it's all going to be computed with Euler exponential splines. So once you've done that, and you've done 100 pages of LaTeX to get all the derivatives and everything else, you can compute everything in n squared log n, all these complicated terms. So what we need is we take the Fourier coefficients of our wave functions, we just multiply them by this d function of Euler, we go back into real space, and this can be used to interpolate the wave function at any point in space. We can do the same thing with our density. We start with our states, put them in real space, we can square them. We can calculate the density and get Fourier coefficients exactly, as we discussed before, in G space, due to the fact that we're working with a DVR. And if I want to do Euler exponential spline interpolation for this, we can equally well do that in order to calculate Coulombic interactions in n log n once we've computed the density in n squared log n. So this EES is really provided a key, and it's part of the speed and parallelism of OpenAtom. So if I want to calculate my my wave function on a little grid, fine grid, inside the core of the atoms, I take the density that I've defined, multiplied by the d factor. I divide it into n little bits, where n is the number of atoms. Okay, I can do the same thing for the, if I want the density inside the little cores of the atoms, and then I can simply do a B-spline interpolation. So these n partition operations are now part of the Charm FFT world. There's still some cleanup work to put in periodic boundary conditions right. But I can produce the wave functions and the electron density very efficiently on a very fine grid inside the atom cores, so that I don't need so many plane waves to describe my system. So in order to implement this, I need to do all these things. I need to create the KS states in real space. That's done. We create the smooth density in real space. We've done that. Just part of normal DFT. Create the smooth density around the ion cores. We know how to do that. That's new. Create the smooth Z matrix. That's already in the code. Create these core densities, which I'll explain to you. So again, we've derived these things. It's a big bunch of derivations, but many of the software packages that we've heard about today are in fact going to require, underneath the hood of the nice bullet points everyone shows, is quite a lot of applied math. So let's just review getting the smooth density. So I take my density in G space, I multiply it by the D factor, IFFT into real space. I do an N partition, so I get the number of the points I need to do the interpolation on the grid. Only those little squares, and I do the B-spline interpolation, and I can get the smooth density around inside all the ion cores on a very fine grid. And that simplifies matters greatly, and the computational complexity is n squared log n. So we can also create these Z matrix elements, these overlaps. So we take the D function, multiply it by the projector, FFT into real space, do a B-spline interpolation, and then we have the smooth Z matrix for ion type. So again, it's an n square log n operation. There can be many different types of atoms in many channels, and we can handle that. So once we have that, we can construct the core density inside of the ions. So we can create this guy, which is simply the core-core interaction, which is going to take these Z matrix elements, square them, multiply them on the fine grid by the difference projector, and that creates the core-core part of our interaction. So if this sounds like there are many terms, there are, and there's even more derivative terms. However, we can do them. So the core density inside the atom, again, it's the same thing. We take our G space, we multiply by our D factor, we go into real space. We get the weighted sum around the atoms. And that gives us what we need, this thing we call core 1 on the atoms. And again, because it uses FFTs, and we can effectively construct everything in order n squared log n. So we have made progress. We have char arrays defined, communications patterns established, and we have the beginnings of the FFT library that we need. We have the flow chart for the energies and the forces, which, if you notice, every term splits into 3 parts. And then with the long range, short range, that takes those 3 parts and splits them into 2 more. And then the forces give you a whole bunch of terms. So we've done some modeling outside of OpenAtom to test the fine grid spacing, the Coulomb clutches, alleviating Coulomb cusp conditions, convergence with real space cutoff, which is complete. And again, this Charm FFT library is being expanded. So we're ready to begin integration into OpenAtom, maybe with new funding. So what could we do? Yep, this is the last slide. I see you. So if we look at a perovskite solar cell, it has lead in it. Lead is a heavy atom. And what's exciting about them is they reach the solar cell efficiency of silicon, but it's a much cheaper material. So it's high efficiency, low cost, but there are problems: instability with air and water, with light, with interfaces, with toxin, and there's toxic compounds like lead. So people are trying to handle all these things, and simulations can help. And we'd like to get into that game. So given we can handle heavier atoms, we can understand the mechanism, we can search for non-toxic high-performance materials and design new interfaces with longer lifetimes. Okay, so that's my conclusions. I'll let you read that, and I'll take any questions if I have time.
Thank you, Glenn.
Virtual clapping.
Didn't see any questions in the Google Doc.
Maybe there's a point, since you're involved, Eric, maybe there's a point you want to emphasize about the computer science.
And so on the computer science side, it's helped us to develop some additional communication patterns in Charm to manage this essentially grid-to-grid communication patterns for subsections of the computation, which we haven't quite formalized to general schemes, but have been implemented in the application. Oh, we have a question from Mills. Goal is to study solar cell materials without having to build them.
So these solar cells exist. So let me see if I can go back. So these perovskite solar cells really do exist. So there's problems in manufacturing, which I don't think we can help with, but there are. But there are also problems with degradation with time and light, and degradation with water. And you'd like to play around with the structures and coatings to try and prevent that damage. And then it would be cheap and low cost. So the problem with solar cells is getting a manufacturable material that will last a long time, 25 years, I think is what you need at low cost, so that it can replace at least some of our electrical capability. You know, light, it depends on the time. It depends on, you know, if you live in Alaska, there are times when you see no sun. If you live in an area with lots of rain, you don't see the sun. But it could be, in effect, a big improvement.
Okay, yeah, so I know very, very little about sort of the details of the state of the solar cell field. So I guess the big problem right now is still that the return on investment is takes roughly the length of the lifetime of the solar cells, and so it's sort of quote not profitable enough. Is that trying to?
Yeah, it's cost.
Okay.
So people have developed better materials as this, which were in principle cheaper, but then they have problems like silicon. People know what to do, but it's simply too expensive.
Right.
So it becomes a cost problem. It's not like they don't work. They in space. You just use silicon solar cells and you're a happy man, because the cost of the launch to get the thing in space is much more expensive than the solar cell. So
right. Once you have a rocket involved, everything else is
chump change, right? But if you want to have them on every house, and you don't want it heavily government subsidized, you have to bring down the cost.
Right, right, and the government subsidy at least is maybe an initial thing, but it's not long-term economically viable. Okay, right.
Yeah, I mean that's always the fight, you know. if the government has infinite money, all things would be possible.
Right. Okay, and so basically here you're saying the sort of the takeaway is trying to leverage Charm++, the scalability, parallelization, and use that then to sort of try to tweak some of these solar cell designs to get some idea of, before you start trying to do everything in a lab, which presumably is not cheap to build all of the different tweaks and variants, you can get some idea of what is worth investigating by using these computer simulations.
Yeah, if you will, it's a kind of discovery project. And maybe you can find a mechanism that's general enough. In other words, you can find some physics. Oh, this thing goes like that, and therefore if I sort of design something like that, it'll be better.
Okay. All right,
All right.
cool. Thank you very much.
No,
thank you.
for asking.